page with the problems that we are supposed to discuss. We can, of course, discuss anything else. So, if you have anything else to say or anything regarding the problem, please do so. And so, I'll just slowly start with the problems. So the first problem is this concerns this F9 that we constructed in the lecture. Let me just recall that. Um, Let me recall that as well. So F9 is so that was what we started with. Yes. So this is the F9. Yes.
Anirban, just to let you
Yes.
know that I'm here and I'll be keeping an eye on the chat. So in case they want to
Okay.
use the
Okay.
chat. Yeah.
Yeah. So please make use of chat box, or I mean, the best thing is to simply interrupt me and just stop me and then ask questions. And so if you don't want to do that at some point, then just use the chat box, and please do so. Yeah, so I'll just continue with this example. So we started by asking. So the initially we had this field of uh, the finite fields with with whose number of elements are prime. So we saw that any z modulo p, where p is a prime, forms a field because every element is invertible. And then we ask the question that do we have fields whose order is not a prime? And an easy example is fields of order 9, and we constructed two of them. In We constructed them in two ways. So one is this matrices, so-called skew symmetric matrices. So if F is a field, then we have this is we define this set S2F to be these matrices, so-called skew symmetric matrices, and then this S2 of Z3 is a field, but for Z5 it's not a field. So that these things are very easy to check. So what you need to check is to just take a matrix and try to invert it. So just suppose the inverse exists, then just multiply these two matrices and see that if you are in Z3, then it is invertible. In Z5, it is not. So that is easy to check, and that was also an exercise. So there is really nothing much to discuss, and that gives us a field of 9 elements. The other one we constructed was like this. So we considered polynomials over Z3 again, and it's a certain subset of polynomials. So it contains 0, 1, 2. So these are just elements of Z3. And then we have the polynomials whose coefficients are coming from Z3. So we have x plus 1, x plus 2, 2x, 2x plus 1, and 2x plus 2. So if you just note that these are all the elements of the form B plus A plus BX. So A and B are coming from Z3. That's what it is. So all linear polynomials, including the constants. So that's the set, and we define addition, just addition of polynomial. You can simply add and then read the coefficients modulo 3. For example, if you add say, yeah, I should have kept some more space here. So if you add this 2x plus 2 and say 2x plus 1, then what, just your simple addition would give you 4x plus 3, and you are reading modulo 3. So this is same as x plus x, just x. The coefficient, the constant term vanishes because it is divisible by 3. So you are left with x. So that would be the addition, and multiplication is and for multiplication, what you do, you multiply and then read modulo x square plus 1. So this is an example. It's better to explain by example. So this is an example we saw last time. So just if you multiply these two polynomials, then of course you read coefficients modulo 3, but you read the entire polynomial also modulo x square plus 1. So if I multiply these two, x plus 2 and 2x plus 1, then what I get is 2x, just by ordinary multiplication, it's 2x square plus 5x plus 2. And by collecting this just x square and 1 from here, so 2 times x square plus 1 plus 5x. 5x is 2x because 5 is 2 modulo 3, and this part vanishes because it's divisible by x square plus 1. So we are reading modulo x square plus 1. So if that's a if that's the multiplication you define on f9, then and the addition modulo z3, then what you get is it's easy to prove that that's a finite field. And we proved last time that the multiplicative group of of non-zero elements of a finite field is cyclic. So the exercise was to find the generator for this. So exercise, the first exercise was to prove that it is generated by 2x plus 1. So once the generator is given, it's not difficult to check. So you just have to raise it to the to various powers to see that. So it is going to, so if you just raise it to the raise powers of 2x plus 1, then you would end up getting all the elements of the field, all the non-zero elements of the field, of course. So that would prove it. But a priori getting a generator is a difficult problem. So even the algorithms, as I understand, is not very efficient. So to find generators, so given a large finite field, it's not easy to find the generator of this cyclic group of non-zero elements, cyclic multiplicative group of non-zero elements. Uh, since it is just direct checking, just raising these to the powers, so I to various powers, so I'm not doing that. So we have more interesting things to discuss. But if you have difficulty checking that, please let me know. We'll do it as well. And so is the other one. So you are so this wants you to find all the square roots, all the elements which has square root. So that's also simple because you just simply take squares of every element, and maybe we'll do some. Yeah, so if you just take squares of every element, then whatever you get is has a square root. So I would just let me just write a few lines of what I am saying. Yeah, so just change the color. So it's just to recall that the elements of F9 are of this form: a plus bx, where a and b are coming from Z3. So suppose so I have say a 2x. So if I raise it to the power 2, suppose, so then it is 4x square. So that is simply x square, because the coefficients are read modulo 3, so that is simply x square. And x square, so we are also going to read modulo x, the polynomial x square plus 1, so this is just minus 1. So we are reading modulo x square plus 1, and minus 1 is 2 modulo 3. So minus 1 and 2 are the same thing. So that would mean that 2 has a square root. So 2 has a square root, namely 2x. So 2x, so 2 square root in this field is 2x. So in F9, of course, otherwise it looks ridiculous. So this is what it is. So and likewise you can try other things like 2x plus 1. So if you raise 2x plus 1 to square to second power, and you have 4x square plus 4x plus 1. So this is going to be x square plus x plus 1. Reading modulo 3, coefficients are read modulo 3, and if I read modulo the polynomial x square plus 1, then it's simply x. So x modulo x square plus 1, and uh, that says that square root of x is 2x plus 1. So in this way you can make a list of element which has square root in F9. So that is simply the exercise. So this exercise is just to make you used to the modulo, the process of going modulo a polynomial. Okay. Mm. Okay. Then so let's try the second one, which says that x cube plus x square plus 1 is irreducible in f2 of x, and hence construct a field of order 8. So this, once we prove irreducibility, we know how to construct. We will discuss both of this. So let's start with this polynomial. So this is the second one. So the first one is not really the full first one, it's just part of it. So just mentioning the number. The second one, so the polynomial is x cubed plus x squared plus 1 in f2. So as we decided last time that we would write fp to fp is equal to zp, and also for any prime power q, we also know that the order of a finite field is a power of a prime. So given any uh, yeah, so if uh, a field of q elements are written like this. So this is a field of a field consisting of q elements, and we know that if there is a field of q elements, then it has to be power of a prime, some prime, some power. So so we are looking at this polynomial. Let's just give it a name, x fx. Now it is a cubic.
Anirban,
Yeah,
may I interrupt for a minute?
yeah, sure, sure.
I mean, I'm answering some questions in the chat box. There is a question to which I don't know the answer.
Oh, sure, sure. I would look at that. Yeah.
Okay. No. I can tell you the question.
Okay.
Instead of you looking at it, let me tell you the question.
Okay.
Okay. So the way I understand it.
Yeah.
So how do you find a cyclic generator of this group? How do you find one?
Yes, yes. So that is in general difficult.
Hmm. Okay.
So that is on in general difficult. Of course, when element-wise checking is an option, but that given a big group, I mean big field of a large number of elements,
Hmm.
that is terribly difficult.
Yeah.
So yeah, so I was actually looking up something. So it says that the available algorithms are not efficient enough. There are some algorithms,
Hmm.
but not efficient enough. I mean, even for a computer, it's very difficult to find for large fields.
Aha. Okay, that's pretty much what I said. I said for small examples, you can do it by trial and error and with some,
Absolutely.
but for I don't know of a general method. Okay,
Yeah. So
so
there are algorithms that I'm not I don't know those algorithms, but also read the comments that it's not they are not very efficient.
they're not efficient.
Yeah, they are not.
Okay,
So
there is another question.
exponential time algorithm kind
Aha, okay. So, but it's safe to say that for our purposes today, it's safe to say that it's not so easy,
of. Yeah,
and
it's
leave
not
it
so
at that.
easy. Yeah, in general, it's not easy.
Yeah, and there is another question, but I will bring that up slightly later because the
Okay,
discussion is going on, and I will at an appropriate time I'll bring it up. Please proceed.
okay, sure. Thank you. Yeah, thank you. Yes, so we now we have a cubic polynomial over some field f, which is f2 here, the characteristic 2 field, and we want to say that it's irreducible. So suppose it is reducible, then what can happen? It breaks into factors. So it's a degree 3 polynomial. So the possibility is either it breaks into a linear and a degree 2, or 3 linear. So I just write, so if it is irreducible, if it is reducible, if fx is reducible, then it can be written as a product of maybe I just erase this and write it in a better way. So this notation we know. So can be written as a product of so first option 3 linear factors. So 3 degree 1 polynomial as a product of 3 degree 1 polynomials. Second option could be one linear and one quadratic. So 1 degree 1, 1 degree 2, and that's it. There are no other option. So no other option to break a cubic polynomial. So since these are the two options, it has to have a linear factor. Therefore, x has a linear factor. Has a linear factor. So if it is reducible, then it has to have a linear factor. And so it has to have a root in f2 as linear factor over or in f2 of x. So everything is happening in f2 of x. So that it has to have a linear factor in f2 of x. And that would mean that it has a root in f2. And so if x has a root in f2. So that makes the job easier. If so, what we proved here is that if x is reducible, say in just mention this as well here. So f2 of x, then it has a linear factor in f2 of x, and consequently it has a root in f2. So therefore, we can simply check that this polynomial doesn't have a root in f2. If it doesn't have a root in f2, then it is irreducible. And that is easy to check because f2 has just two elements, so it is just 0 and 1. So it's modulo 2. So these two classes. So if you put 0, then you have yeah, you have 1. So f of 0 is 1, f of 0 is 1, and f of 1 is 1 plus 1 plus 1 is 3, and that is again 1 modulo 2. So it doesn't have a root. So f doesn't have a root, and therefore it is irreducible. So once you have it irreducible, then you can construct by, so the construction was just the construction done in the theorem. uh, so we take the polynomials. So construction was like this. So ax, two polynomials, I keep the same notation. In fact, this was the notation in the theorem. So ax and bx in f2 of x are equivalent, or okay, let's me write it like this, that for ax and bx, we say that these two polynomials are related. So we define a relation, we define a binary relation on f2x like this. So if they are related, if ax minus bx, so just the module, just just like modular arithmetic, so is divisible by, done for polynomials, so divisible by the polynomial x cubed plus x square plus 1. And this is going to be an equivalence relation, which is what we have proved in that class. So if you just simply find the representatives, so the thing is to find the representatives. So this is just let me write that. So this is going to be an equivalence relation. Equivalence relation. And the equivalence classes would form a field of order, and so equivalence classes so field of order 2 to the cube, so which is 8. So this 2 to the q is what we had in the theorem, is this q to the degree of the polynomial. So that is what it is here. So you get a field of order 8. So that's the construction. So you have to find the equivalence classes. So I will go to the next one. Yes. Next one is very simple, but it's very crucial. It says that if P is the characteristic of a field, then x plus y to the P is equal to x to the P plus y to the P for all x and y coming from K, coming from this field K. So this is not difficult. So because it's just take this x plus y. I would just mention this as well. I just add a page. I think I'll just add a couple of pages. So K is, just change to my usual color. So K is K was the notation. So K is a field of characteristic P, then x plus y to the P. So if you expand it using binomial theorem, then you have many terms. I'm not writing because you also don't need to write. Just this observation would be enough, that all these terms have coefficients which are divisible by P. So
Uh,
in fact, the first one is,
Anirban,
yeah,
can I make one more interruption,
yeah, sure,
please?
sure, sure.
So before you go on to this,
Hmm.
so another question about the generator. There was a slight, I think, confusion in the questions in the chat box. There are. I tried to explain it in the chat box, but maybe it's worth clarifying it. You
Yeah,
could do it. So there
sure.
are two meanings for a generator. Generator of the field, for example, x in your example, where
Yes.
you took f3x, was it, or f3x by x square plus 1, right? Modulo x square plus 1. That's
Yeah,
what you were checking.
yeah,
Uh, x, for example, generates the field,
yes,
but not it's not a multiplicative generator of the.
yeah, right,
Uh,
right, right.
so uh, generator has two meanings. Here, what you mean is it should generate the cyclic group of
Yes, it should generate, yes, of
it
course. So
should be a generator of the cyclic group. That is a stronger condition than saying that it just generates the field.
of course,
Yeah,
yes, yes,
yeah. Just to clarify. Yeah,
yeah, yeah, sure.
yeah. Thanks. Go on.
Oh, yeah. So, okay. Uh, Uh, yes. So, so we were just looking at this x plus y, x y coming from the field. So for x y coming from the field, x plus y to the p. If I expand into in binomial, then this the first term is x to the p, and last term is y to the p, and it is enough to observe that all the intermediate terms will have coefficients which are divisible by p. So coefficients of, so this observation is enough. So coefficients of all intermediate terms are multiples of p, and coefficients are, so that amounts to saying that p divides p choose r for for everything 1 less than equal to p less than equal to, sorry, r p minus 1. So for all r, so this simply follows from this fact that p divides p choose r, the combination coefficient p choose r, and therefore all these terms, all the terms between x to the p and y to the p have coefficients which are divisible by p, hence that they are all zero modulo p, and the characteristic of the field being p, they would all vanish, and you would end up getting x to the p plus y to the p. And the comment accompanying the problem was that if you define this map to be some elements a going to a to the p, so just raising element to the power p, that would be an field automorphism. So the additive part comes from this observation, and multiplicative. So it is multiplicative homomorphism is obvious, of course, and it is commutative. So no problem in showing that a b power p is a power p b power p. That just follows from commutativity, and this part additive part follows from this observation. So some more problems. Yeah. Yeah, so these are some yeah, so two more irreducibility, some variations of this. So this is x square plus 1 is irreducible over fp if p is of certain form, that p is 3 mod 4. For example, 7 is the first prime in that form. And this is another example where x square plus x plus 1 is irreducible over fp when p is 2 mod 3. So so I mean, these are easy things. So as such, irreducibility is not very easy to check all the for everything. uh, Again, for smaller field there is one type of algorithm, for larger fields there is another type of algorithms, and it's still not so there are efficient algorithms, but there is some non-triviality in that. uh, so I would just start with let's discuss these two questions. X square plus 1 over fp and x square plus, yeah. Okay, I think somebody has written something on this page by mistake. So can you please erase that? Yeah, so I can't erase it because it belongs to somebody else. Yeah, so I just forgot the problem number. So yeah, that is problem 4 and 5. So we have this polynomial x square plus 1 over fp. So suppose it is reducible. Suppose x square plus 1 is reducible. So as we argued previously that being a degree 2 polynomial, so we argued for degree 3 polynomial, it's going to be the same. So it has to have linear factor, and therefore it has to have a root. So it's true for both degree 2 and degree 3, but no, for not for higher degree. Degree 4 polynomial might decompose into two quadratic polynomial, none of which may have roots in the field. So a degree 4 polynomial might be reducible without having any root in the field. That's possible, but for degree 2 and degree 3 it's not possible. They have to have linear factor, and and therefore roots. So it is reducible. So therefore There is an alpha in Fp whose square plus 1 is 0. So alpha square plus 1 is 0. And that says alpha square is minus 1. And so alpha power 4 is 1. Therefore, the order of alpha, so order of alpha is obviously a non-zero element. So I tried it in detail. So alpha is so alpha belongs to Fp non-zero element. So we are always writing it like that. That Fp without the zero, without just subtracting the singleton set 0, and order of, so order is not 2, so it has to be 4. So order of alpha is 4. So that's multiplicative order. So just this is order of alpha in the multiplicative group of non-zero elements. So which we wrote like this. So this is a cyclic group, and order of the group is p minus 1. So it just misses one element, namely 0 from the field. So it's p minus 1. And alpha is in the group and its multiplicative order is 4. So therefore 4 divides, so order of an element divides the order of the group. So 4 has to divide p minus 1, and that shows p is 1 mod 4. And that was precisely the condition we took just to avoid this situation. So we took, if so we said if p is 3 mod 4, then it is irreducible. So if p is 3 mod 4, so being a prime, you have only two possibilities: either it is 1 mod 4 or it is 3 mod 4. Yeah, so we also say that it's not 2. Let's say it's not 2. So if p is 3 mod 4, then this is not, this doesn't happen. So x square plus 1 is irreducible. It cannot be reduced. Same for the other polynomial. I'll do that too. I keep forgetting the polynomial. Let me just recall that. X square. Mm, x square plus x plus 1. So should I just stop sharing and share it again, because just reshare, because that some line is there in I so
Okay, sir.
it's impossible to remove it. I mean, I can't remove it. So there is some lines on the place. So I'll
Okay, sir.
Okay,
just
sir.
stop share for a moment and then reshare.
Okay, no problem.
Yeah.
Nirban,
Yeah.
so Annamalai has been asking lots of questions on the chat.
Okay. Okay.
So maybe
More of things. So at most.
no, whenever you feel the time is right.
Yeah. So I'll just finish these two problems because there are only two left. So I just finish this and then we discuss that.
Sure, sure.
Yeah, this last problem is interesting, and this first one is actually the next one is quite easy. I'll just do that too. So x square plus x plus 1 over fp. So we do the same thing. Yeah. So okay, I also have a list of this. So don't have to look at this. Yeah. So x square. So now the polynomial is x square plus x plus 1 over, or let's write in the ring f in fpx. So it this has a bit of a trick. So x is so you can, if you just look at x cubed minus 1, then you can write it as x minus 1 into x square plus x plus 1, and that factorization remains valid here. So I'm just taking p to be, say, greater than 3. Yeah. Uh, okay, maybe I should have written it the other way around. So suppose, let's write it for you. So suppose this is just write a full argument that this is reducible in fpx, then so again the same argument, since it's a quadratic it has to have a root, so there exists alpha in fp such that alpha square plus alpha plus 1 is 0. So x so now the factorization, so we use this, that alpha cubed minus 1 is alpha minus 1 alpha square plus alpha plus 1, and that is 0. So alpha and alpha square both are not 0, obviously. So alpha cubed has to be 1. So alpha cubed is 1, and so it has to be the order of, so that says the order of alpha in the multiplicative group, if p multiplication, so in that multiplicative group is 3. Therefore, so just same as the previous, so the order of this element should divide the order of the group, which is p minus 1, and therefore p is 1 mod 3. So if we simply avoid this condition, we just take a p which is 2 mod 3, then this will become irreducible, and that is the polynomial. That's the situation we looked at. So I would just switch to the last problem. What was the number for that? Okay, so I also wanted to mention this. Okay, so we have been doing by this trick we have been doing the only quadratic polynomials. So, but that this trick is more effective, in fact, in certain cases. So I would just suggest this. So this is an exercise within exercises. So you may try this. So you can consider fx equal to x to the 4 plus x cubed plus x squared plus x plus 1 in fp. fp of x, and suppose also that, and so or write where p is a prime bigger than 5, so at least 7, and p is not congruent to plus minus 1 mod 5. So then it is irreducible. So then fx is irreducible. Or I can just write it like this, that if p is greater than 5 and p is not plus minus 1 modulo 5, then fx is irreducible. So it also has same trick. So I would just say a bit of hint of this, just hint for this problem. So the trick is again to write this. So trick which was employed in the last problem works here as well. So use this. Yeah, so use this. So if f doesn't have a uh, so if f has a linear factor, if it has a linear factor, it need not have linear factor. So if it has a linear factor, then we have, so it has a root, then we have element of order order 5. So if it has a linear factor, then this the above this relation with this equality is going to give you an element of order 5. And if it does, yeah. So the next thing is that, and then it would just follow from this. So p has to divide 5 has to divide p minus 1. So p is 1 mod 4. That's not possible if we take, oh sorry, this is not this is not congruent. uh, just write that. So 5 divides, so in that case 5 divides p minus 1, and so p is 1 mod 4, 1 mod 5. So if we assume that it is not 1 mod 5, then this case is settled. But this being a degree 4 polynomial, it might break into 2 quadratic polynomial. So how do you handle that case? So if fx has 2 quadratic factor, in fpx, yeah, so if it has 2 quadratic factor, then it's going to have a root in a quadratic extension of fp. So then fx, so a degree 2 extension of fp, degree 2 quadratic extension k of fp, say. So let me elaborate it a little bit. So what I'm saying is, if fx breaks into two irreducible polynomials, say, two quadratic polynomials which are irreducible. Let's call them ax and bx. So both quadratic, both degree 2, and irreducible. So if they are reducible, then it of course has a root. If they are not, then that is the question. So that then we need to do this argument. Degree 2 and irreducible. So then just consider uh, okay, so I mean, last time we just discussed about splitting field. I mean, just discussed. Of course, we haven't proved, but we are also assuming the existence and uniqueness of that. So you can always find a field where it has root, and this is a degree 2 irreducible polynomial. So you would find a field where it is going to have a root. In fact, uh, this fp of x um, modulo this the maximum. So this is an irreducible polynomial, so it is going to be a maximal ideal. So this quotient ring is going to give you a field which would be a degree 2 extension, and that is how you construct. uh, we can actually elaborate on this a little more, but splitting, we need this idea so for our lectures as well. So this is a construction. So what I want to write is, then there exists an extension of fp, extension k of fp of degree 2, where ax has a root. So yeah, so it comes with a bit of an assumption. So with that assumption, just assume that there is a field extension where you have roots, and if you have a degree 2 irreducible polynomial, then there would be a root in a degree 2 extension. So we have an extension of degree 2 of k of fp, which is of degree 2, where it has a root. Now k is an extension of degree 2. So it's a field. So if you draw like this, then you have this fp, and here you have a k. So these are also, so both of them are fields. This contains, k contains fp. So that's it. So K is a vector space over Fp and the dimension is 2. So dimension as vector space, dimension is 2. So K is a two-dimensional vector space of Fp. So this is P square. In fact, we use this argument to show that every finite field has order power of a prime. So to show that, we use this argument. So it's a similar, it's the same argument. Here the dimension is just 2. So this is so number of elements. So the multiplicative group is going to have a order p square minus 1. Going to have order p square minus 1. And if so, we have to also show that 5 cannot divide this. So if this 5 divides p square minus 1, then 5 is 5 is either plus 1 or minus 1 mod. Sorry, then p is either plus 1 or minus 1 mod 5. And by excluding these possibilities, we say that this polynomial is irreducible. So that's simply the. So this is an extension of the same argument. I mean, just I tried to show that it works for polynomials of higher degree also, of course, in certain nice situations. Okay, so we are running a bit late, so just let me do the other exercise as well. Just change the page. Yeah. So just want to. This is the last one. Okay, so what should I do? I can maybe the last exercise I can do later because there are lots of questions. We can discuss them first. That's better. So if yeah, so I can just postpone this one to the next tutorial. This is a bit interesting and slightly longish to discuss. This I just remind that exercise. So this is the x to the 4 plus 1 is irreducible over Q. So that's the first thing to show. So there are two arguments on that. One is an elementary argument, and other is a slightly sophisticated argument. So we can do that, and so it's going to take a bit of time. But the interesting thing is that this is reducible over any finite field. So we would show that will it will require a little bit of a proof. So we do it next time, I guess, in this 6. And of course, the further note that is that's just that's a fun. Just a funny observation. So that it's reducible over R. But obviously it doesn't have linear factor over R. So this is just for fun. So the first part is what requires work. So I'll go for questions then. So should I check the chat box?
Okay, sir.
Yeah. So
the chat box is a little complicated. You could, but
yeah.
I can
Yeah, sure.
It's easiest if you ask. There were some questions by Annamalai. Most of them by
Annamalai. Then Annamalai is welcome to unmute and ask directly.
Yes, that is better.
Yeah. Yes, sure. We can start a discussion. Yes, please.
Yeah. Okay. So actually, my question is, I forgot my first question.
Yeah.
So I asked, it is possible to construct a field from polynomial ring in two variables.
So you have a polynomial ring, say R of xy. Yeah.
So is it possible to construct field from this polynomial ring? Sir replied that we can find some maximal ideal.
Yeah, of course. So the
But
main thing is to finding maximal ideal. Yes.
but here maximal ideals are just a polynomial in single variable, ideal generated by a single variable, right?
Yes.
But this is not a PID, sir. So that result will not work here, right? So R by M is filled if only if M is maximally. So for I think
Ideals in these rings can be complicated. Yes.
Yeah.
So.
Yeah.
Otherwise, instead of taking y, R by x comma x square or something.
What do you mean x comma x square?
That is another variable. Anyway, we call it polynomial. The unknown is x and x square. Maybe you can call y. That is not a matter. Okay.
No, but if it is x and x square, then that is the same as Rx, right? If you join x square, Rx already contains Rx square, x square.
Yeah. You cannot have x square. Yeah.
No, sir. It's a polynomial contained terms only x and x square.
That is not a ring. That is not a ring, right? Because x into x square is what then?
Yeah, so you are saying the polynomial, it contains only some bx and cx square. Only quadratic polynomials.
Oh, no.
So if you multiply them, they don't remain quadratic.
So okay, better we call it y.
Yeah. Better we there is no option. We cannot. Yeah, we have to. If we are bringing a variable, then it have to be.
Yeah. So if it's a polynomial ring, that just means it's R adjoined some variables, right? So here is something. So this is maybe we should not entertain this question too long because it's a long story, and so. But here is something maybe connecting to what we have been studying. Here is a question. So for example, you could ask, you take F3, for example, adjoin X and Y and go modulo X square plus 1, for example, and then another polynomial in Y, say Y cube plus Y plus 1. So Anirban, if you would be so kind as to write this.
I just missed the first one.
Yeah, take F3.
F3.
F3 just for, or FP, put a P to be more. And then, for example, adjoin X and Y.
Yeah.
And then go modulo some polynomial in X, say X square plus 1.
Yeah.
And one other polynomial that you had in mind, X cubed, X square plus X plus 1.
Yeah.
But that is just same as, that's maybe not good. Make it X to the 5 plus X to the 4 plus X cube plus X square plus the one you had.
Okay.
And just for example, you can generate more examples.
Cyclotomic.
Sorry, make it Y. Sorry, this I meant to be in Y.
Oh yeah. Okay, yeah. That's yeah, cyclotomic.
Yeah. So you can ask what if this is going to be, whether this is a field, for example. This would be a question that is worth asking. And how do you determine such what is happening? So essentially what is happening here is this FP x modulo X square plus 1 is already if X square plus 1 is irreducible in your FP x, right? In one variable FP x square plus 1 is irreducible. Then you see FP x by X square plus 1 will be a field.
Yeah, so FP of X and suppose that is the case.
Let's say FP,
suitable P, that, so this is already a field.
Yeah, suppose this is a field, then it is just like asking over that field whether this polynomial is irreducible.
Yeah.
So you can sort of bootstrap this way. Okay. And in general, if you have any commutative ring and go modulo maximal ideal, you will get a field.
Yeah, so
sort of, that is sort of.
Yeah, so if you call that K, then what you are trying to say is that
this thing you can write
find irreducibles on that.
Yeah.
So that would be an way. So find irreducibles in KY,
Yeah.
and
And in,
then take quotient.
then take quotient, for example.
Yeah.
Okay, you can.
Yeah, that's the kind of thing one can do. Yeah.
Yeah, and I think going in further into this question will take us too far afield from what we are doing. I think we can. Okay, Annamalai, you had anything else?
Yes. Okay. So therefore, order of the field is p power degree of the polynomial first one, and then degree of second one, right?
If this is the case, if this is the case.
Yeah. If the other one is irreducible, yes, then it would be yes, because just by vector space argument.
So therefore, given any irreducible polynomial in x and irreducible polynomial in y, we can produce a polynomial of we can produce a field of order p power degree of the polynomial x into degree of the polynomial y.
Degree power x.
Given, so you are taking the xy plus 1 is one of the irreducible polynomial. And then this cycloidal polynomial is another irreducible polynomial. Therefore, we construct a field.
No, see, the thing is, this the other polynomial should be irreducible in the field K.
Yeah, no, he's saying that if it is irreducible, then.
Okay, if it is irreducible, then
This is one way. So from this we can construct field.
Yeah, you can construct a field.
Yeah.
From the reverse, okay, this is not a only way. If you
Yeah,
take
so
this
that
is
would
not
that polynomial should be irreducible over the new field K. The second
yes,
polynomial y.
yes, new polynomial. Yeah, right. It should be irreducible over the new one.
Okay, so yeah, okay. So that is one question, and then what the next question is?
I think we should, Anirban.
Yeah.
I think we should. I mean, we are over time, so my suggestion would be people who want to leave may leave, but we can stay around and answer questions
Sure.
if they want to
Yeah,
stay.
that is of course. Yes.
Yeah. So Gurusamy, if people feel free, let them leave if they want to.
Okay,
but,
okay, sir.
Anirban and I will be here, and we'll be happy to answer questions.
Okay, sir.
Okay, sir. Okay, sir.
Yeah, they're welcome to stay around, no problem. But
Okay, sir.
at the same time, if they have work to do, we are over time, so they should feel free.
Okay,
Okay,
sir. No
sir.
problem.
Okay, go ahead.
So, and the one more question is we construct in the beginning, we construct a field using matrices.
Right.
Etc.
Right.
And after that, we construct the field using the polynomial.
Yes.
So, is that the only method to construct a field from polynomial thing? So, Ramsa said it's a standard one.
Yeah, that is a very standard one. So we just simply take an fp of x and then so any field in fact, and then
Only for finite field we can. This is the only standard method.
Yes. And finite field, what we would prove if the degree is so if you have this fp and if you construct a field of an extension of degree say r, then it's going to be unique up to isomorphism. So we would call it fp to the r. So that would be unique up to isomorphism. So finding various ways of constructing is as such of not much of theoretical use at least, because they are going to be isomorphic.
Yes, okay. My question is, so this is the only way to construct a field using polynomial. Without polynomials, it is possible.
No.
Yes.
So that is, nobody is saying that is the only way to construct. We are not saying that. Okay. So this is the standard way to construct. I mean, what you're asking is a good question, but I don't think we want to commit to say that this is the only way to construct. No.
Maybe there can be other ways.
Yeah, there can be. Tomorrow you may find a new way of constructing. No, that is always open to.
Yes. So I am asking the existence ones.
Yeah, this is just. I mean, so what do you mean by ways of constructing? There are, perhaps a different way of thinking about the same object could lead to a different construction. What we are saying is that this is one standard way to construct, and what Anirban just said is, look, there is only one field of that cardinality up to isomorphism. So once you have constructed it, you know it exists. So theoretically, at least, you are not looking, so to speak, proactively for other means of construction. You know it exists, and then if you construct it in some other way, okay, it's some extra bit.
No, it might have some other practical application. I mean, it's possible. So
Yeah, absolutely, that's true. That's true.
some other construction might have some really significant application. That's possible. But theoretically speaking, once we have this, and since it is unique up to isomorphism, we happily settle there.
But you can look for other means to construct.
Sure.
Yeah, yeah, as you said. Yeah, I
And
think
then
we
there
understand.
can be, I guess there can be practical applications. I'm not sure. I really not aware of that, but could be.
Any other questions?
Okay, so we know that any two finite fields are isomer, the same order if it is isomer.
Right.
So if you take the infinite field, but the characteristic is P,
Yes.
it is isomer.
No, far from it. No,
Infinite.
No. For example, there is something called transcendence degree of a field. So, for example, if you take FP adjoin one variable x and take its quotient field, FP adjoin two variables polynomial ring and take its quotient field, those two are not isomorphic, for example.
But these both are finite fields, right?
No, they are not finite fields.
No, they are not.
They are finite characteristic fields.
So you are taking that rational field, right?
Yeah, I am taking rational functions in one variable.
Yes.
Okay.
And then rational functions in two variables. That is,
Oh.
I am taking the polynomial ring in one variable and then taking its quotient field. I'm taking the polynomial ring in two variables and taking its quotient field, for example.
Yeah, their characteristic is finite, but not
characteristic.
They are not.
Yeah.
In fact, about this irreducibility, so I am thinking of doing something about irreducibility in my last lecture. Discuss some algorithm for irreducibility.
So irreducibility of a polynomial over a finite field.
Yes, of course.
Okay.
So I mean, I don't know, and people might be already familiar with that. There's this Barley-Combs algorithm. So I'm just thinking.
I am not familiar with it. So
Okay.
So is there any criteria to check irreducible in two variables? Any criteria?
Any criteria? I do not know actually. Even for single variable, it seems quite. It seems a bit tricky. So, I mean, as the degree goes up, I mean, for larger degree.
no, what I guess anomaly means is like Eisenstein criteria or something like that.
Yeah.
Okay. Which will work for certain field, certain polynomials.
Yeah. For example, P taste or.
Right. No, I don't know.
See, you can have that Eisenstein criteria in the rational field. If you have the rational field FPX, and then take a polynomial in over that, right? And then you can have a criteria like that, Eisenstein.
But I think it's only the polynomial over Z, right?
That is what, instead of Z. So instead of Z, you can have a you can make that, that is actually over Q, or in other words, over Q.
Yeah.
So instead of Q, you can take FP of X.
Okay.
And then you see, essentially you can do that over any PID kind of thing.
Yeah.
So, but anyway, maybe that is taking us beyond
So you
beyond
can
our
do it
scope.
over Q, so you just replace then this Q by FP of X and then attach some.
Yeah, and then take, for example, over irreducibles over FPX, you could have an Eisenstein criteria.
Yeah. So anything else from anyone else?
Yeah.
I think no questions,
Finite
sir.
field cannot be algebraic closed field, right, sir?
Sorry?
Finite fields never algebraic closed field.
No,
No.
they can never be algebraic.
Never. Never. Yeah.
Okay, thank you, sir.
Okay.
Thank you, sir.
Okay,
Thank you
maybe
for
we
the
can
nice
meet at 5.
interaction, sir. Both of you, sir. Thank you very much.
Yeah.
Thank you. See you at 5 then.
Ah,
Okay, sir.
sir.